In our last class period together, we came up with a definition of a system and looked at several different examples. So what you're going to do in this module is go into a little bit more detail about types of systems, components of systems, and how matter and energy flows through those systems. If you want to pause the screen and read the assessment statements that go with this content, feel free. Systems are interactions between both the living or biotic and non-living or abiotic constituent parts. We are going to discuss inputs, how those inputs are processed, and the processing of the inputs leads to outputs. And every system is going to have inputs and outputs. One example of a system is photosynthesis, and we are going to refer to that several times throughout the year because it is the starting point of all food chains. The inputs into photosynthesis are sunlight, water, carbon dioxide. That light energy is trapped and processed by the chlorophyll, and the outputs are oxygen, water, and glucose. Photosynthesis can also be considered a system within a system. If you remove one of these organisms, or each organism, and put them in a pot or a cage, they're not going to be able to survive on their own. The plant needs the solar energy to undergo photosynthesis, which produces chemical energy in the form of glucose for the herbivore, and then the herbivore passes that energy on to the carnivore. So if you remove any one of these components, the system will break down because it's the interactions between each of the components that make the system, not each individual component themselves. Now, I said that all systems have inputs and outputs. That is the case for open systems. They're going to exchange both matter and energy with their surroundings. So matter and energy is input, and matter and energy is also an output. So examples of open systems, pretty much any system that you think of is going to be an open system. An ecosystem, you have solar energy input, you have nutrients input from our cycles, and you also have the same outputs. You've got energy usually in the form that's been converted through photosynthesis, passed on as glucose, and then passed from herbivore to carnivore. You have nutrients. When animals decompose, those nutrients are passed out of the ecosystem, so that would be matter. One example would be nitrogen in the nitrogen cycle, and we'll go through the steps of that later, but that is one example of something that cycles through an ecosystem. A closed system has inputs and outputs, but only energy, not matter. These systems are extremely rare. There are no systems on Earth that are closed systems, but we can think of the Earth of itself as a closed system. Light energy enters the Earth, and long wave energy, or in the form of infrared, is re-radiated from Earth's surface. So that would be energy as an input and an output. The only matter that enters Earth is if we are, hit by meteorites, asteroids, something along those lines. But Earth is generally considered a closed system. We have made several attempts to create closed systems on Earth. Biosphere 2 is one example. We have yet to be successful. This particular one was built in Arizona at the end of the 80s. And the idea was that if we could create this on Earth, then we could transfer that technology to, the moon, another planet, because at this rate we're going to use up Earth's resources. The problem was they never were able to produce enough food to sustain those that lived inside, and they often had issues with the oxygen levels as well. So we haven't perfected this as yet, so we still are struggling with creating a closed system within Earth. An isolated system is the only type of system that has no inputs or outputs. You probably can't think of an example because they don't exist. The only thing that would be considered an isolated system would be the universe as a whole. The next thing we're going to look at is energy specifically, how it flows through systems, and it has to follow the laws of thermodynamics. Energy can be in the form of light or in the form of heat. It also can be stored in the bonds of organic molecules. The first law of thermodynamics says that energy is neither created or destroyed. So what that means is the energy in the system is going to be constant. Whatever energy is present before is going to be present after. Now it can change forms, but the total amount of energy remains the same. So if we look at photosynthesis in the terms of the first law of dynamics, first law of thermodynamics, the energy that enters the system is a form of light energy from the sun. And then through the process of photosynthesis, that energy is converted into chemical energy in the form of glucose, and then heat energy that is released as well through respiration. The second law of thermodynamics states that when energy is converted, it is degraded to a lower quality, less useful form. So it usually is going to be degraded into heat. So our input energy is used to produce useful energy or work, but you're always going to have some loss or some degradation of energy, and in that conversion process we're going to lose that energy as heat. So looking at our same food chain, we start with solar energy, and that energy enters the plant. It's the energy needed for photosynthesis. The plant is going to convert that into glucose or chemical energy, but it's also going to release that heat during the work, and that's where the respiration comes into play. Animals consume the chemical energy from the plant. They are going to generate heat during work. That's your animal respiration. That's why your body temperature is warmer than your surroundings. That energy is getting converted into heat. And then as we move along our food chain, the lion eats the zebra, the energy is passed along, and the lion also loses some of that energy due to respiration. In addition to respiration, in the attempts to escape the lion, or the lion using energy to catch the zebra, you're also going to have chemical energy that's changed into useful work. Because we are losing heat at each level of the food chain or in systems, nothing is ever going to be 100% efficient. Most plants have about 2% efficiency. That means of the solar energy that hits the leaves of the plant, about 2% of that's converted into glucose. The rest is lost to the ecosystem. Herbivores, when they eat the plants, about 10% of the plant energy they consume is used for useful work. The rest is lost in respiration and other metabolic processes. Same thing with a carnivore. So you're essentially passing only 10% of the energy to each level of the food chain. So take just a minute, pause the video, and see if you can figure out what the carnivore's total efficiency in the food chain would be. Alright, hopefully you converted the 2% to a decimal, the 10% and 10%, and determined that the carnivore only uses about 0.02% of the incoming solar energy that hit the original plant, or the grass in the case of the food chain that we've been looking at. The rest of the energy is dispersed into the surrounding environment.